Hello everyone, I am Trivedi from LJ Institute of Engineering and Technology, and today we will learn how the practical of whirling speed of shaft has been performed in the lab. So it is a practical of the subject the dynamics of machinery, and let us start our basic introduction. Now, what is the aim of this practical? So, the aim of this practical is to determine the whirling speed of a rotating shaft. Now, if you see the diagram, there is the image of the whirling speed of shaft apparatus. This is known as whirling speed of shaft apparatus. Okay, this apparatus I will explain in our next slides. So now let us start the introduction of whirling of shaft apparatus. As you see at here, this is our whirling speed of shaft apparatus. Okay. Now, if you see the whole system, this is the basic apparatus and which is connected with the variac. Now, what is the variac? Here there is a motor and the motor is connected with this variac. This is basically the voltmeter, which can increase or decrease the voltage which are transferred to this motor. So this is the whirling speed of shaft apparatus. This is the shaft at here. So now, if we want to understand how the system works, first of all, we have to understand the basic theory of whirling speed of shaft. Now here there are different criteria. Likewise, there in the engineering, we are using the vertical shafts, and basically in approximately each and every shaft or maximum shaft whatever we are using, they are of the horizontal criteria. Hence this practical is very important for us. Now for the horizontal shaft, we have to understand how the rotation takes place and what is the deflection and how we can calculate the speed of the shaft, or we can save the shaft for the failure. Now here there is a shaft, as you see. I show you the simply supported, but there are different kinds of the inclination or the attachment. They may be fixed, they may only simply supported, or one part fixed and another simply supported. There are different kinds of fixing attachment which we are using. Generally they are fixed with the bearing only. Now, let us assume there is a shaft and there is the rotor at exactly at the center of the shaft. So, here, whenever this rotor, if we see at here, the CG of this rotor is slightly deflected, and that deflection is considered as eccentricity E, if, as you see at here. Now, let us consider the rotor. Now suppose the shaft rotates with omega angular velocity. So the rotor will also rotate with the omega angular velocity because it is rigidly fixed with the shaft. Okay. Now let us start. If this rotor rotates with omega angular velocity. Now let us assume that the CG is at here. So if we just see from the side view, we will assume that CG, the position of CG will be at here, and the total mass of the rotor is will tend to act in the downward direction, as I show you, that is mg. Now let us assume that this G is making angle omega t with this rotor. Now how it is so? As we all know, this CG is at theta angle. Okay, and theta is equal to omega by omega into t, because omega is angular velocity by time, and we have discussed this criteria so many times during our lectures. So here the angle is omega t. So if we want to consider this horizontal distance, it is completely depend upon omega t, and the value at this instant is E cos omega t. Okay, now let us have the another motion. It means suppose G is at right side of O. It means it is rotating in anti-clockwise direction. If you see, now if this will rotate in anti-clockwise direction and we have CG at the right hand side, then what will happen? The motion is in anti-clockwise, but due to the weight of this rotor, it will retard the motion. Okay, and it will retard the acceleration. Similarly, if we study about if CG, because it is rotating, this disc is rotating, hence the position of G will be changed with respect to the speed. So here, when CG is at left side of it and omega is anti-clockwise, hence acceleration will be there only. It means this weight will increase the speed of a shaft automatically. Now, by this, what will happen? If we see at here, there is the CG point, the mg will retard the motion, weight of this rotor will retard the motion slightly. And when we put, when the CG will slightly move at this position, it means at the left hand side, this mg will accelerate the motion. It means by continuously doing this kind of practice, what we can assume that the speed of this shaft, it means the deflection will start at the half of the rotation of the speed. The total theory is explained in my lectures. You can check my YouTube videos for that. But basically, because of the CG position, we can assume that because it is the horizontal shaft and changing in the CG position, we can assume that the shaft will start vibrating, or the frequency will be there where there is only half of a speed occur. Okay, this is known as half frequency whirl. Now we have already learned in this theory, but let us study the practical kind. So for this practical, we have to consider the frequency of a shaft. Now frequency values are different. We say, suppose if they are fixed, there are the fixed bearings, then we have to take the frequency equation like this: Fn is equal to 3.562 under root of GEI upon WL raised to 4. Now if we consider the different frequencies and different values or different contacts of the bearing with the shaft, then the frequency equation will be changed. But for our course of conduct, we have to only consider this frequency equation for the fixed support. Now here there is, what is W? So W is the uniformly distributed load. So basically it is kg by meter. Now what is L? L is the length of a shaft. What is E? Which is Young's modulus of elasticity, and this value is constant. We will take 2 into 10 to 11 Newton per meter square for the mild steel material. We are using the mild steel material for our practical. So Young's modulus of elasticity value is 2 into 10 to 11 Newton per meter square. Here I, which is mass moment of inertia, and the equation of mass moment of inertia is pi by 64 d raised to 4. Now, what is the rotation of a shaft? If we will find it, the rotation of a shaft will be N is equal to frequency multiplied by 60. This will give us the value of the rotation of a shaft. And what are the original rotations for the horizontal shaft? So, they must have N by 2 RPM. It means whatever the value we are getting N, practically we will approximately getting half of the speed. Why? Because of the CG value, because of that weight which we have already explained in our earlier slide. Okay, so now let us start system. So for our system, as you see, this is a shaft. Okay, and here we have the bearing. So here I show you the bearing video. This is the fixed bearing. Roller bearing is there, and roller bearing behave as a fixed support for the shaft. So this is the bearing, and here we have the motor. We have a 1/6 HP motor we are using, and this motor is connected with the variac. Okay, so this is our system. Now Let us consider the shaft detailing. So for the shaft detailing, as we know, it is attached with the fixed bearing. So here, if we calculate the with the vernier caliper, the diameter of a shaft is 6 mm. Okay, and the length of a shaft, as you see in our diagram, it is the length of a shaft is 800 mm. So we are taking 800 mm long shaft and 6 mm diameter shaft. Okay, so now let us start the procedure for the practical. Now let us consider the shaft detailing. So as you see, I measure the diameter of a shaft with the help of a vernier caliper, and it shows us at here, if you see it very clearly, it is 6 mm diameter. And as you see in our second video, the length of the shaft is 800 mm. It means if we consider it in meter, it is 0.8 meter. We can use a different length of a shaft as well as different diameter of a shaft. And the bearing, as we all know, they are fixed bearing. They are considering as a fixed bearing. The length from here to here, this point is 800 mm. Okay, we have added this portion also because the rotation is from this point. We are calculating the rotation from this point. Now, because they are the fixed bearing, we will only get the single wall. If we will take the simply supported kind of shaft or journal bearing, then in that case we may get more than two walls in the shaft. Now, let us consider the procedure for the practical. So what is the procedure? First of all, we have to fix the shaft, okay, at both ends very properly, because when it starts rotating, it will be very dangerous for us to control that shaft. So we have to fix the shaft properly. Now we have to check whole apparatus, because see, basically the shaft is rotating, and when the shaft is rotating, vibrations starts, and when the vibration starts, each and every equipment will start to be loosed. Okay, they will lose because of that vibration. So we have to the tightening the screws, we have to tighten the shaft, we have to check each and every component of our material and our apparatus, which have to be fixed very well. Now then, first we need to increase the voltage slowly up to the maximum level. Okay, and the maximum level should be there. We have to take 100 and 120 up to 120 volt for the maximum level, and then we need to slowly down the speed and the voltage, so that we can see the proper, we can observe the whirling or the bending of the shaft. Now we need to observe the loops which are appearing in the shaft, and we have to note down the number. But in our practical, we are using the fixed bearing. In our apparatus, we are using the fixed bearing, hence we will only get the single loop. Now slowly bring the shaft to the rest, okay, and switch off the supply. So this is, repeat the same procedure for the different shaft. Here in this case, I am showing you only the single one. Now I mentioned that here, because both the ends are fixed, we will only can see the single loop. Now let us have our procedure. So for this, let us increase the speed. I am increasing the speed, as you see. So here, by increasing the voltage in the variac, we can we can get the increased speed in the rotor. Okay, now here our motor will starts rotating, and it can transfer load to the shaft, as you see in our in our video. So here if you see at here, we are putting our system at the maximum speed, and here the whirling starts. If you see, we get the whirling of the shaft. Okay, because this is because there is a fixed bearing, we can see only a single whirl, and here we are getting the maximum deflection. Now for this we have to take reading. Here I attach the contact type tachometer with the motor end point of the motor. It is at the very end at our system, and we have to measure the maximum speed in this contact type tachometer. Okay, so let us check. We attach the contact type tachometer at the with the motor so that we can find out the speed. You can see at here the number, and it is 1581, which is the maximum speed for our shaft, for this shaft. So here whirling of shaft is very dangerous for each and every mechanical component or automobile component. As you see, I am decreasing the speed at here. Okay, by decreasing the speed we can see directly that how the whirl starts, and if you see at this point there is very less whirling. Okay, and this is known as the initial deflection of the shaft. This is known as the initial deflection of the shaft. We have to calculate the rotations or RPM with the help of contact type tachometer or non-contact type tachometer, so that we will get the practical values. Okay students, so this is our practical. Now how to take the readings? First of all, we have to fix both of this bearings. Then we have to fix the shaft at the bearings, and then we have to give it the maximum speed, and then we need to decrease it. Okay, so by decreasing that speed we can measure the rotations of this shaft. So here there are we have taken 6 experiments, and each and every shaft is having different weight. Depends on the material property. We are taking the material as mild steel only, and there are different diameters. The diameter, I have to say that we are taking 3 different diameters. The diameters are 4 mm, 5 mm and 6 mm. We have taken 2 different types of lengths. So one length is 0.8 meter and another is 1 meter length. So for each and every shaft we are taking the same, and we have calculated the mass for each and every shaft. So here there are the masses. Okay, now we need to calculate the weight of a shaft. And what is the equation for calculating the weight? It is mg by L. So by calculating this mass m multiply by gravitational acceleration g divide by this length, and we are getting this kind of values. Okay, and then after that we have to calculate the mass moment of inertia. So what is the mass moment of inertia? It is 1.25 into 10 raised to 11 for 0.004 mm, 0.004 meter diameter. So for 5 mm it is 3.06 into 10 raised to 11, and for 6 mm it is 6.36 into 10 raised to minus 11 Newton, minus 11 meter raised to 4 mass moment of inertia. Okay, so here these are our practical analysis. Now the second analysis. So here we have the practical data for the speed. It means initially whatever I show you the for the diameter of 0.8 meter length and having the diameter 0.006 meter, and we get the speed of the shaft as 840 rpm. Okay, this is our practical data. Now let us have our theoretical data. Student, you first of all you have to understand that for this practical it will take approximately a full day, because we need to fix each and every equipment, we need to fix the shaft, and we have to take each and every data nearly 3 times for different shaft, and we have 6 shaft at here. So I have calculated each and every rotations for our shaft. Now let us compare theoretical and practical data, and let us consider, is all that data are okay, or they are perfectly okay or not. Let us check it. Now for this frequency, Fn is equal to 3.562 under root of GEI upon W L raised to 4. Now I have already explained what is G, what is E, and I, W and L. So here we will take the data for the first point, that is 4.8 meter diameter and 0.006 meter diameter, 0.8 meter length and 0.006 meter diameter. So here let us calculate the frequency value. So for this, our frequency value is 14.74 hertz. We get the frequency value as 14.74 hertz. Okay, theoretically. So what should be the rotation value? So the rotation of the shaft should be as 1654 rpm. But at what speed we are getting the values? So here, if you half of this value, what is it? We are getting the practical data as, because we are taking step number 4, and here we get the practical data as 840 rpm, and theoretical value is 1654 rpm. Okay, so now let us check it. If we will get the half of the value for say 1654, it is approximately nearby 830 rpm. Okay, if you calculate this, so we are very near with this original data. So students, we can check for different diameter of a shaft, and in our practical session, and we can easily compare the half frequency one. So student, this is our data, this is our whirling speed of shaft apparatus. If you have any query, feel free to ask me. Thank you so much.